Briefly, what we have. So we have a fixed G mod H over spherical. So H included in the parabolic subgroup, which is in fact the normalizer in G of H, and P mod H is a torus, or in other way, we have H is equal to the intersection of kernel of character of P. And then we have M, which is a lattice generated by the chi I. So it's isomorphic to the N. We have N, its dual. And we have also, so we see that M is in fact related to the function which are semi-stable under the action of the Boris subgroup, and so we have a map sigma from the set of bistable divisor irreducible divisor to N. So in particular, we have a set from D to N, where D is a set of colors. So a color is a bistable irreducible divisor of G mod H. And here we can take so we can take a bistable divisor of X also. So with a G stable divisor, it will also work. So now let me define first a colored cone. So I did not NR by the R space generated by N. So it will be a pair consisting of a cone and some colors. So F is included in D, so which is S minus I in our spherical case. So the colors are parameterized by the simple roots S minus I, and P equals Pi. And C, so it's a convex cone. So generated by the image of the alpha for alpha in F, and finitely many other elements of N. And we have yes, and here we have that C is strictly convex. So it means that it contains no lines, or there's no lines in C. And we have another condition, it's that sigma alpha is non-zero for all alpha in F. So in our case, sigma alpha is the co-root restricted to M. Okay, so we have just so we have a lattice N. So maybe 0 is here, and we have some image of the colors, and we can have the same color at the same place. So the two colors can have the same image. So sigma is not injective here. So here I draw the picture where we have 4 colors, and 2 of them are on the same points. And then I can take a cone. So I can take a cone generated by this point. Generated by this point and this point. Okay. So here we have f is equals to gamma, and we can also sorry, it's not gamma, it's delta. So we have 4 colors, so alpha, beta, gamma, and delta. Beta and delta have the same image, and I can choose to color, for example, delta. So we can have f equals to gamma and delta, and this is for the cone with these colors, so gamma, delta, and generated by these points and this color. So we can have a color in the interior of the cone. But so here we could also color beta. For example, we can also have the same cone with a different color. So we can have beta, delta, and gamma. So we can have also the same cone with different colors. So gamma, beta, and delta. And we could also have so the same cone without colors. So same cone. So f equals. So there's also other possible case, but we can't have alpha as a color because alpha must be in the cone. So the cone is generated by the image of the colors plus other points. So alpha can be a color of this cone. Okay. So that's the possible case.
What's the meaning of this? Finite many elements, right? Is some arbitrary or?
Yeah, arbitrary element. So here I choose this point, for example, but I could have choose other points, so arbitrary points. So these points are arbitrary. So in fact, not if we start from orospherical embedding, but so for the definition of colored cone, so it's it's very arbitrary. Just the color are fixed. So the color and the image of the color are fixed. So it's fixed by the choice of Gmod H, and then so you can have these as colors in the cone.
So basically, you just choose any convex cone.
So you choose a convex cone, and then you look at the color inside the cone, and you can color them or not. So yeah.
And then you select some color inside.
Yes, you select some color. So and you don't select the points, but the image of the colors, but the colors. Yeah. But well, still now I will for the picture to simplify the picture. I will always suppose that sigma is injective, so we have not one point corresponds exactly to one color. Injective. Okay. So just to simplify the pictures. So now, second part of the definition is a colored face. So it's just a face as a cone. So C prime is a face of C, and F prime is just the set of colors in F such that their image are in the face of C, the corresponding face. So for example, in the the yellow case. So we have two colored faces of dimension 1. So this one without color, and this one with the color gamma. So in the yellow case. And we have also one cone of dimension 0, which is the point 0. And one cone of dimension 2, which is all the cone itself.
Always have dimension 2, then? So you said that the line is one dimension.
Yes. So,
true?
sorry?
Is it always true? So if you have a line, does that mean that we have one dimension line in a cone?
The rank of n is arbitrary, right?
The rank of n is the rank of the Gmod H. So it's the same. But so the dimension of the cone is not necessarily the rank of n of the lattice. We can have a smaller cone. So as for toric varieties, so I studied so in R2. So I gave yesterday the example of the half line, and so we got the half plane as a dual cone, and then we obtain C star cross C as toric varieties. So here also I draw a picture where n is of rank 2 and the cones also of dimension 2, but we can also have a dimension 1 cone. So it's answer your question? Yes.
The rank of Gmod H is the same as the rank of Pmod H?
Yes. Yes, the small n, yeah. The small n is yes. And then we can define a colored fan. So it's a finite set of colored cones. So that every face, every colored face of a colored cone. So it's finite set F. Cone of F is still in F. So stable on the taking colored faces. And the second assumption, so it's like in for toric varieties. So it's just to say that for all x in an R, there exists at most. Sorry. Yes, there exists at most one colored cone C F such that X is in the interior of C. So I did not see with a 0 up, so on the top of C as the interior of C. So it means that we can't. So all cones will intersect into a common face. So we can't have collapse. We can't collapse in their interior. So maybe I draw a picture. So we'll have the lattice N. And then I can choose, so I have some colors. So I have 0 here. I have some colors, alpha. Yes, and then we can have a cone, like this. Can have a cone like this, and several cones. Yes.
What do you mean by rank G mod H? Rank G mod H.
The rank of P mod H is the dimension of P mod H. The dimension of P mod H is isomorphic to a torus. And so it's the n here, the rank of G mod H is the n here. Sorry?
Right, right.
What's the rank of G mod H? What's the definition of rank of G mod H?
Right, he finds that rank of G mod H is rank of P mod H. Right.
Generally speaking, what's the definition of rank?
Of rank for spherical variety in general. So it's the so I think it's
not group theoretic.
it's the minimal dimension of codimension. Yes, the minimal codimension of an orbit under the unipotential radical of a Boris group. So it's not very nice as definition, but in general case, it's a definition.
Or gave an example as an 18 SSC, the upper diagonal with diagonal entry with
One.
one.
Yeah. Yes. Okay. So here I draw a picture where
So maybe you can take this for the SSC case. Can you take this?
so for SM2.
For the dimension of rank. Maybe
So for SL2 mode, the matrices with 1 here. So this is isomorphic to C2 minus 0, in fact. And in that case, so this set of matrices, so this H is equals to the kernel of which I call omega alpha. So the unique for SL2 there is a unique so S.
dimension is 3 minus 1. If it's a dimension 2, 3 minus 1. SL2C, I know.
So I don't understand what you. Okay. So in this example, so the rank is 1 because we can SL2 mod H is can project it to SL2 mod B, and SL2 mod B is P1. And then we have C2 minus 0 projected into P1, and so the fibers of this function are C star. So here we have n equals 1. So it's n. So the rank is easy. So maybe it's more clear now. So on the rank of the variety is the same as the rank of n, the same as the rank of m, and so it's all is the same. Okay, so I drew an example of a picture. So of a fan, a colored fan. So it's a fan. So here I decided to draw a fan, a complete fan. It means so it's cover all the space, but I can also erase this one and not take this part, if you want. And now I have some color, so maybe this is a color and this is a color. Well, that's a fan. So we have all dimensional, two-dimensional colored cones. And we have all edges, so we have these edges, these colored cones with gamma as colors. We have these colored cones without color, this colored cone without color also, and this colored cone and 0. We have all the cones in this picture.
So this is equivalent saying that you just have a fan in fluid geometry and then some collection of
Yes.
colors
Yes.
inside.
Yes, it's equivalent, yeah. So I just define colored faces because it will be useful as for toric varieties to have a correspondence between G orbit and the colored face for the the element of the fan. So all the colored cones and their colored faces. So it describes all G orbits. So now let me give the relation between colored cones and colored fans and Gmod H embedding. So I take X, Gmod H embedding. And then I look at, so I can write X as a union of X, Y for Y closed orbit. So G closed orbit. So the X, Y is defined by the set of X in X such that G, so the orbit of X contains the closed orbit in its closure. So it's equivalent in the toric case to take sub-affine varieties of the toric varieties. So here, so we cover X by XY, which are not affine, but they are called simple embeddings because they contains only one closed orbit. So it's the definition of simple embedding. So only one closed orbit, closed G orbit. So we can cover X by such XY, and for each XY, we can associate a cone CY and FY as follows. So we take the so Fy will be the set of alpha in S minus I, such that so the bistable divisor in Gmod H, so we take its closure in X, and it contains, when it contains the closed orbit, we say that it's a color. So if I draw a picture, so we have Gmod H here, and we have X, which is here, and then we have some we have some divisor outside. Yeah. Okay, so we have some divisor here. So which corresponds to the divisor. So we have G-stable divisor. So irreducible G-stable divisor, which I denote by X1, Xm. And we also have so the D-stable divisor, which are here, and so we have maybe this divisor. And if we have a closed orbit here contained in the alpha, then we say that the alpha is a color of X, or of the fan. And so we have the red divisor here also, so we can use them to define the cone. So CY, so it's a cone generated by the colors, or by the image of the colors. So by so sigma de alpha for alpha in Fy, as in the definition, and the sigma of xi for I equals 1 to n. So sigma is also defined for G-stable divisor in X, and so we have also an image of images of these divisors in N, and then we take all sigma alpha and all sigma xi to generate a cone.
How do we define sigma xi?
Yes, so sigma was so So sigma was from G mod H B minus 0 mod C star, which is isomorphic to M. It goes to Z. And it was defined by the degree of 0 on poles on the divisor D. So you can define it on every B-stable divisor, and G-stable divisor are B-stable. So you can...
You define the sigma as from colors to N.
Yes, so first I define sigma from colors to... so this is defined from colors to N. It is defined when we fix G mod H and we don't look at X. And then here I have to give me an X to define all. So to define a sigma. So to define sigma on all. So I can extend it to the divisor on X if I fix X and X. So yes. Okay, so if this it's okay?
I think about it later.
Yes. So it's the same definition. So we take a B-stable divisor, so either a color or a G-stable divisor, and then we define sigma as the variation which gives the degree of zeros or poles along this divisor of the function, and it defines a map from M to Z, and so it's an homomorphism from M to Z, so an element of N. Okay, so for the colors, we have a nice description because it corresponds to the dual, the co-roots restricted at M, but for the Xi we have no nice description. You have only the description I write there. So now to X we can associate it all Cy and Fy plus the colored faces. And then this map defined a map from G mod H embeddings to the set of fans, so colored fans. So I claim that this construction defines a colored fan, and then this map, so it's a theorem of Luna and Wust, is that it's a bijection, so it's a one-to-one bijection, so one-to-one map. So here I have to mod out by isomorphism. So I say that, in fact, embeddings are a variety with open orbit G mod H and a point, and we say that X and small x is isomorphic to X prime and small x prime if and only if there exists a G equivariant map phi from X to X prime, which sends the point X into the point X prime. So this is an isomorphism of G mod H embedding, not of G variety.
This theorem is for spherical.
So, in fact, this is also true for all spherical varieties, but I have not defined yet the colored fans for spherical varieties, so there is more to say. But this is true for all spherical varieties when I will have defined all things. So, if we apply these results to to toric varieties, then we will have we will not have exactly the same correspondence between of toric varieties under isomorphism and fans under automorphism of C-stars. We have less than that, because so for toric varieties, so we can, there's no color, so we have a lattice and we can take another lattice. It does not matter. So you will have, so you can apply an automorphism of the lattice and it does not change anything. But here you can't apply an automorphism of the lattice, because you have some partial points here which are fixed. You can't move them. So that's why here we can't take the colored fans up to automorphism of the lattice. So you can't have this. So here you have less than in the toric case. So in fact, if you want, you can take the automorphisms which fix the image of the colors. So in that case, it will be only the identity. But if you have only one color, you can have automorphisms which fix this color, and then we can have isomorphism also here as a G variety. Well, it's just a technical point here in this result. So this result is very nice because we have also properties as for toric varieties. So for example, we can say that X is complete if and only if its fans is complete. So if it covers all the space. We also can we also have a bijection between G orbits of X and the elements of the fan, so the colored cones in the fan. And so in particular we have the Xi, so the G-stable divisor corresponds to, so irreducible, corresponds to the edges of Fx which are not generated by a color. And here I precise a color of X. So what I call a color of X or of Fx, it's alpha, which is in F for some CF in Fx. So as for toric varieties, we have a description of the Picard group of X. So we can say that it's generated by so the Xi for I equals 1 to M, and so the G-stable irreducible divisor, and also the colors. So the colors of G mod H, so all the colors here, not only the colors of X. So even the colors which are not colors of X, all the colors. And we have also N relation, so infinitely many relation, but n-dimensional relations. So it's like for the toric variety. So for all chi in M, we will have relations. So like this. So maybe okay. So here, for an edge which is not generated by a color, I denote by xi the primitive element on the edge, corresponding to xi. Maybe I draw a picture. It will be better to understand. So you have a fan. And you have some edges which are generated by colors, and the other which are not generated by colors. So this is one color and two colors. And we can have also gamma, which is not a color, and etc. And also delta, if we want. Okay, and then. So if you fix, yes, if you fix an embedding, you fix a colored fan. Yeah, so Gmod H embeddings and colored fans are in bijection. So it's the result of lunar and boost. And then, so here you have two, x1 and x2, and I denote x1 here and x2 here, the corresponding primitive elements. It means the first lattice point in the alpha line here. And then for all character in M, so in the dual of the space where lives the colored fan, I can say that the sum of chi xi times xi plus, so it's I equals 1 to M, and here it's a sum over all colors of chi and alpha M times d alpha. So d alpha is the divisor, the b-stable divisor corresponding to the color. So, and this is equivalent to 0. So these are all relations that we can have in the Picard group of X. So we have n relation because the rank of M is n.
Which divisor come from the another P?
This divisor, the d alpha.
Also come from
Yes. So by abuse of notation, I denote d alpha and the closure of d alpha in X with the same things. So it's so here when I say d alpha, it's the closure of the b-stable divisor of Gmod H in X. So normally d alpha is the b-stable irreducible divisor of Gmod H. So it comes from Schubert's variety. So it's the inverse image of the Schubert variety of codimension 1 of Gmod P by the map which sends Gmod H to Gmod P. Okay, so we have n relations. So in particular, if X is Q factorial, so we can express the Picard number as so M plus the cardinality of S minus N minus N. And we can also rewrite it as so the number of edges of Fx. So here I denote all edges, also those which are generated by a color. So I have always minus n, and then so I have too much edges here because I count the edges corresponding to the M divisor, Mg stable divisor, and also some colors here. So here I have to add so the cardinality of S minus I minus the cardinality of the colors, which I denote by dx. So dx is a set of colors of x. Okay. So the set of colors which appear in the colored fan here. Okay. So this expression is more is nicer than this expression, because here we have two positive. So if we suppose that x is complete, here we will have something which is greater than 1, and here something which is positive, because dx is included in S minus I. Okay. So we use this expression to study all spherical varieties of Picard number 1, and spherical varieties also. So it's also true for also. So here I make an assumption of regularity, so we can express. So we have some criterion to say if a variety is cofactorial, or if it's factorial, or it is smooth. So we have a smoothness criterion, which is due to me and Timashev at the same time. So we obtain the same result at the same time. And a corollary of this criterion is that if we take so every G-stable subvariety of a smooth or spherical variety is still smooth. Okay. And this is not true for spherical varieties in general. So that was already known for toric varieties, and for all spherical varieties it's true, but not for spherical varieties. So remark, not true. So I don't write here the smoothness criterion because it's very, very long to write. And so yes, there's the first point is that if x locally factorial, it implies that all cones are generated by a basis. So C is generated by a part of a basis. And we have to add some condition of the colors to have the inverse inclusion. But the smoothness criterion for locally factorial or equivalently Q factorial is only use the picture of the colored fans. So we use only the point in the lattice and the colored fan. So we only use combinatorics here. But for smoothness criterion, we have to use we have to look at the G we look at and the parabolic subgroup in G. So we have to look at the Dynkin diagram of G and which are the color exactly which place they are in the Dynkin diagram, and so that's why for smoothness criterion it's more complicated. Okay. So what I can. So here I just generalize the result I already told for toric varieties. So yes. So we can also express the anticanonical bundle. So an anticanonical divisor. So an expression of the anticanonical divisor is the sum of the xi as for toric varieties plus the sum for alpha in S minus I R alpha d alpha, and this is the expression we add for flat varieties. So if we look at only at flat varieties, we have this part, and if we look at toric varieties, we have this part. And the alpha, so our coefficient greater than 2. So they are expressed explicitly. So there is an explicit formula for this in my case. So this is only for all spherical variety. So there is an explicit formula which I don't write.
Is this exactly anti-canonical one of G mod P?
Yes, this is the canonical of G mod P. So it's minus G mod P. If we so here the alpha will be for G mod P the Schubert variety, and this is the inverse image of the yes, and this is will be the part of toric varieties.
Is that T alpha is numerically effective still?
Sorry?
Numerically effective
Yes.
T alpha.
So
Still in X.
yes. Yes, of course. Yeah. So it's the closure of the divisor in G mod H. So to take the closure, and it's irreducible. And okay, and then we also have a criterion of Cartier and ample divisor. So this result is also true in general, and it's due to Brion. But in general, we don't have this R alpha greater than 2, and we don't have an explicit formula. So in general case. So yes. So another theorem of Michel Brion. So we take D equals to so the sum of Bi xi plus the sum of B alpha D alpha. So we take a divisor and then we can tell if D is Cartier or not. So D is Cartier if for all colored cone in Fx, so there exists an element of M such that for all yes, so for all xi in C, so the primitive element corresponding to the G-stable divisor, we have xi times KC equals the coefficient here, and for all color in F, we have the same, but with B alpha. So I did a mistake when I said that the Picard group is generated by the xi and d alpha. So it's true if the xi and the d alpha are Cartier. So maybe just suppose that x is locally factorial, and then so it will be true. Okay, so we have this. So it's defined in particular for all cones. Will define KIC, an element of M. So it's defined a piecewise linear function. So linear on each cone. So it's just a KIC on C. And so then we can say when a divisor is ample or not. So then if D is Cartier, we have so D is ample if and only if HD is strictly convex. So yesterday I tried to explain what means strictly convex, but I did also a mistake in explaining this. So maybe the better definition of strictly convex is to say that for all x in so for all C and C prime cones, so C, F, and C prime, F prime, so colored cones of Fx, and for all x is in the interior of C, we have that so chi C of applied to x is greater than chi C applied to chi C prime applied to x. So this is the definition of strictly convex. So there is an equivalence with polytopes. But, sorry? So it's the definition of strictly convex. No, there's no inclusion here. So it's every couple of face. So you take one cone, you take an x inside, and it says that the function chi C is so the value in x is maximal for chi C, and for all chi C it will be less than this. And if you erase strictly, it's just say that it can be equal. So we have this condition and a second condition we didn't have in the toric case. We just say that for all alpha which is not a color, so for all alpha in so for all cones, and for all alpha which is not in F, we have chi C of alpha dual must be strictly less than the B alpha. Okay, yes, it's this. So we have conditions on colors here to be Cartier, and for not colors, for alpha which are not a colors, we have a condition for ampleness here. Okay. Okay, so it's just a generalization of what was known for toric varieties. So maybe, okay. So I just want to generalize another thing I told about spherical, about toric and flag varieties. So it's the construction of all spherical varieties starting with polytopes. So projective all spherical varieties and polytopes. So let me give maybe. Well, I'll just. So remember, for flag varieties, I just take one simple G modules, and I embedded the flag varieties in the projectivation of this projective space. So. And for toric varieties, I take a sum of C, which are simple C star n model. And here I will mix both of them. So I will take, so I can't take only one dimensional G model because G is not a torus. So I take G models and I sum of some polytopes in M. So here I take a polytope in M. I take a lattice polytope, so which lattice points as vertices, and I construct in this projective space. So I take the so I take. So for toric varieties, I took the particular point which was 1, 1, 1, 1, 1, 1, and for flag varieties, I just took the eigenvector, so the highest weight vector of weight chi, and here I will take a sum of all highest weight vector, and I will take the closure inside the projective space, and it will give me in a lot of examples projective all spherical varieties. And in fact, it will work if the polytope is not too small. So maybe one example. So yes, okay. So I take G equals SLN. I just take a segment omega alpha I plus 1. So there is two lattice points in Q. So we have the sum of these two G modules. The fundamental representation, so G modules of for G equals SLN, and so I took the orbit of this vector. So I take the wedge product of E1 and EI plus the wedge product of E1 and EI plus 1. So, and I take the closure of this. So we can remark that this space is isomorphic to gamma I plus 1 of C n plus 1. So we just add an element. So if we take x plus z, so this is in wedge I Cn and z is in h y plus 1 Cn, and we just associate E0 wedge x plus z, and we take E0 such that E0 plus Cn equals Cn plus 1. So we just add one vector to have one dimension more, and then by this map we have this isomorphism. And in particular, this map sends this vector in a vector which is also decomposable. So we can also write as the wedge product of I plus 1 elements, and these elements are plus 1, and here we have a plus or minus 0. And in particular, this element is in the Grassmannian I plus 1 and n plus 1. If we look at the Grassmannian I plus 1, n plus 1 in by the Plucker embedding in the projective space of this module. So if we note x equals to this, then we have proved that x is included in the Grassmannians of I plus 1 and plus 1. And in fact, they have the same dimension, so we can compute the dimension. So, in fact, we have an equality here because of dimension. So, because the dimensions are the same. So, we can remark that so this variety, which was a spherical variety, so we can compute the. If you want, you can compute the stabilizer of this point, and you can see that H, so the stabilizer of V omega alpha I plus V omega alpha I plus 1 was the kernel of omega alpha I minus omega alpha I plus 1 in the parabolic subgroup defined by, so maybe I can, so defined by PS minus alpha I plus 1. So it's just this is the intersection of two maximal parabolic subgroup. So we can check this very easily. So we add an spherical varieties, and under a bigger group, in fact, the varieties is homogeneous. So we can have something like this. And maybe I can give another. Okay, so I try to go quickly. So I take 0, omega alpha, omega beta. So I think I take SL3, yes. So here I take SL3, and I look at G times 1 plus V omega alpha plus V omega beta in so P of so C, which is the representation associated to the weight 0. And plus some C3 plus lambda 2 C3. So by the same trick as before, so we have this is isomorphic to C2 of C4. And then, so it's an exercise. Maybe you can prove that X is a cone over a Grassmannians, so of vertex 1, 0. So X is cone of vertex 1, 0, 0, and 1 plus 0 plus 0, and of bases, so of base. So G, so the Grassmannian 2, 4. Embedded in P of the external product of 2 times of C4. So it's the same computation as here. So you prove first that X is included in this cone, and then by dimension, by argument of R dimension, you will have the same property. So and by this way, you also construct polarized or spherical projective varieties. Okay, so in general for spherical varieties, it's not the same. So because we don't have the property that for all spherical varieties, it's defined by the intersection of kernel of characters. So it's tell you that you can here choose highest weight vector, and for spherical varieties in general, you can't choose highest weight vector. You have to choose other vectors, and which are not so well known as highest weight vector, and then you obtain different things. Okay, so I had no time to speak about the general case, so maybe I will speak about this tomorrow morning, and I will also give examples. I think it's a very nice examples because we look at all the difficulties we can have, and we can compute also all. So it's very simple and very complete example. So I will do this tomorrow morning.